So we're back. Solubility values are what we just looked at, and you see that there's a pretty big difference in solubility values for different kinds of compounds. From things where 100 grams of water might dissolve 4 or 5 grams of the substance, to things where 100 grams of water will dissolve nearly, 175 grams of the substance. And it's all down to how soluble they are. There is also a solubility table in your book on page 404, but I'll be giving you pieces and copies. Actually, if you're somebody who is interested in looking at solubilities, I found by hook and by crook the Chemical Engineer's Handbook. I can't remember the publisher, but there's like one Chemical Engineer's Handbook that's like the Chemical Engineer's Bible. And it has got extensive solubility tables on it. So if you're a chemical engineer and you're designing a system where you're going to be creating solutions, you need to know what your solubilities will be at given temperatures, because you may be designing a machine that puts in a given volume of water to a given volume of solute. It has got solubility values for every chemical I could think of in one place. The new editions of this thing are a couple $100. If you're a chem engineer, you're working someplace, your employer has probably purchased it for you. However, and I think they're on the 9th or 10th edition, you can get the 7th edition for free online. It's available as a PDF. I downloaded the whole darn thing. And it's got all kinds of chemical performance data, including really extensive solubility tables. And I think it's a pretty reliable source. Wikipedia's got a big solubility table. I'm not sure what the source of that information is, so tread carefully. But if you can find a chem handbook, Chem Engineer's Handbook, that's a pretty good source. So the first thing is that affects solubility is what kind of solvent and what kind of solute you're looking at. It has to be the perfect marriage. We said water's the universal solvent, but water doesn't dissolve everything. If you think back to the lab we did with ionic and covalent compounds, phenyl salicylate does not dissolve in water. It's a covalent compound that is non-water soluble. There are other things that are non-water soluble. In general, ionic compounds are highly water soluble. Water will not dissolve most things that are nonpolar. So that's your oils and greases and fats. And if you've ever tried to rinse oil off your hands with just water, it doesn't work. It does not come off easily. On the other hand, ionic compounds generally don't dissolve in nonpolar solvents. So, has anybody here ever taken apart a greasy anything? Greasy lawnmower engine, car engine, wheel bearings. Okay, you should all go at home and find something to tear apart. Seriously, you should. It helps your brain, it changes your brain. So, in most auto shops, there is something called the parts washer. And the parts washer is where, parts get washed. I know that's completely counterintuitive. Those parts are covered in grease. There is dirt in the grease. In order to get those parts clean, you have to put them in a solvent which will dissolve the grease. When I was growing up, when we changed wheel bearings, my dad rinsed out the wheel bearings in gasoline. You're not supposed to do that. But it's a great solvent. It's fantastic. It gets the grease right off. Water won't work. There are other commercial solvents. I don't know the names of any of them, but they are all these nonpolar solvents. Some of them are things like toluene, probably. A lot of these nonpolar solvents, like gasoline, toluene, are also known carcinogens. They are known cancer causers. And mechanics are one of the trades that have higher than you would expect rates of some cancers because of exposure to solvents. Carbon tetrachloride, CCl4, is one that we use in kill jars in biology. So you put we call it carbon tet, you put it in the plaster of Paris in the bottom of a jar, put a lid on it, catch your insects, you put them in the kill jar, you screw the lid on, and they die in a few seconds. The joke is always, don't take a deep breath. Carbon tet also used to be used. It's a fantastic solvent. I know someone whose mom was a drafts person in the 50s. She started off doing drafting in World War II because the guys were at war, and she managed to keep a job through the 50s. And they used carbon tet to clean their tools, to get the graphite off the tools. And she ended up dying of a cancer that was probably related to her carbon tetrachloride exposure. When dealing with those kind of solvents, you want to be careful. Now, thinking about those solvents. The parts washer is very often a closed bin. It's full about halfway with solvent of some sort. It has a, hinged lid of some kind. You put the parts in it, and it gently agitates the solvent around the parts. What factors there are getting the parts clean? Because what's actually happening? You are creating a solution of the grease that is on the parts. That is the solute, and the solvent that's in the parts washer. Now, if the solvent is being gently swirled around the parts, what is that doing? Okay, describe it in terms of solubility. Things that increase solubility. What? Agitation. Agitation of the material, because you're increasing the number of collisions between the solvent and the solute. The grease is the solute. Now, there comes a point when the parts washer, my cousin's a mechanic, he'll say, solvent in the parts washer is shot. It's done. What is he saying in chemical terms? What is true of that solvent now? It is saturated. You now have a saturated solution in the parts washer. It cannot absorb any more solute. And so there is a chemical company that comes and they swap out the stuff in the parts washer. And those people probably also have some fairly high occupational risk for cancers. We know more than we used to. A friend of mine who worked as a mechanic in the 70s and 80s said, "Oh, I love the taste of asbestos. It's always sweet on your lips after you did a brake job." Ooh, nice. We know more than we used to. We're more careful than we used to. But solvent-solute interaction matters a lot. Not all solvents will dissolve, not all solutes. I am going to post a video link on this very topic because I have this song stuck in my head and I want to share my joy with you. So that will be posted after class. Okay, typically, and we sort of touched on this yesterday, we think about solutions mostly as a liquid that is dissolving a solid, and the liquid is the solvent and the solid is the solute. But we have solutions that are in fact liquid-liquid pairings. And the terminology we use in this case is a little bit different. If you have made salad dressing, you know that the oil and the water separate. You have to shake them up. They don't stay dissolved. They don't stay in solution. When we're talking about liquids, we say that they are immiscible. And when we talk about liquids that will dissolve one another just fine, they are miscible. So ethanol and water are miscible. Propanol, which is rubbing alcohol, and water are miscible. If not, we couldn't have a 10% solution of propanol. We would have a layer of pure propanol and a layer of pure water, and that's not the case. And again, this comes down to polar-nonpolar interactions very often. That's okay. All right, so big discussion about pop and the solubility of gases in liquids. Okay. Okay, last idea, and this also relates to pop. Pop is a great thing to talk about with solutions. So, the warmer the temperature, the less gas you can dissolve into a liquid. And I had a friend in college who, if we all got pizza and pop, the rest of us would just open the pop off the shelf at the store and stick ice cubes in it. And he was absolutely adamant that you could not do that. Had to go in the fridge. If you had to put it in the freezer for 15 minutes, that's fine. I don't care if you don't have pop with your first piece of pizza. Because what he knew, we all knew, but we just didn't care, was that the colder it is, the more gas that liquid can hold. The bubblier your pop is. You can cool the liquid down, but that room temperature liquid is going to hold a lot less carbon dioxide than cold liquid. So if you open it at room temperature, much more carbon dioxide will escape immediately than if you open it when it's really, really cold. Solids and liquids, more or less predictable, but a little bit less so. Generally, the pattern that you saw on your solubility tables holds, and the warmer the solvent, the more solute you can dissolve in it. There are a few very minor exceptions, but they're so minor that they don't even really bear talking about. In general, increased temperature means that you can dissolve more stuff. Okay, tomorrow we will pick up talking about the concentration of solutions and one more kind of math.